This is our Amitec Electronics RFT-04A FM-IF amplifier. It consists of a ceramic filter at the input of broadband amplifiers. So, as a result of which, the center frequency of the total amplifier is centered around the frequency of the ceramic filter, which is working at a center frequency of 10.7 megahertz. The bandwidth of this filter is roughly about 250 kilohertz. We can apply AGC voltage to increase or decrease the gain of this particular FM-IF amplifier. Now, in order to observe its characteristics, we have connected the tracking generator output to the input of the spectrum analyzer, and we can see a straight line. The level right now is roughly about minus 27 dBm or about 80 dB microvolts from the tracking generator. We are deliberately using this level because it falls in midway to the range of the amplifier. If we reduce this level, we'll go into the noise floor. If we increase this level, the amplifier might start compressing. So now right now the level is roughly about 4 graticules from the noise floor of the equipment. As we connect the tracking generator output to the input of the amplifier, and we connect the spectrum analyzer input to the RF output of the FM-IF amplifier, we observe that there is no gain in the circuit. The moment we apply AGC voltage, we see a huge amount of gain in the amplifier. We are right now observing a bandwidth of about 500 megahertz, but our desired frequency of interest is 10.7 megahertz. So we will try to change the center frequency and try to zoom in to the desired frequency. As we can see, this forms our center frequency, and we can observe that this center frequency is our desired frequency of about 10.7 megahertz. If we change the voltage, we can change the gain of the amplifier. Right now the gain is roughly about 20 dBs. It is 10 dBs right now, and it goes down to 0 dB, and after which the gain goes into the negative. We see that if we increase the gain more than about 30 dB, the amplifier starts to clipping, because its output is right now compressing at a level of about 110 dB microvolts or about plus 3 dBm. When the amplifier starts compressing and the noise floor starts to increase, because of which other frequencies will be passed through and it will stop blocking the other frequencies. So we have to reduce this noise floor so that there is maximum level between the passed frequency and the blocked frequencies. So we can measure. So we've been able to see the compression point of the amplifier. If we increase the tracking generator signal, the output stops behaving linearly, and there will be a point wherein the gain starts to reduce by about 1 dB. So that 1 dB will form the 1 dB compression point of the amplifier. We can zoom into the circuit and we can measure the bandwidth. Right now we can see the 3 dB bandwidth is our scan width is roughly about 200 kilohertz. We have about 2 graticules from the peak we have to measure the frequencies. This is one of the frequencies and this is the other frequency. So we can see the difference in the two frequencies roughly about 400 kilohertz. So this is the bandwidth of the amplifier.